and welcome to episode number 22 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, we're going to wrap up some sample problems and then wrap up the whole course by talking about virtual machines. But before we get started, and before we even talk about our OS of the day, a couple bits that we should discuss first. In our last episode, I mentioned that today would be the series finale. But I sat there and I thought about this afterwards. And I said to myself, you didn't pay for 22 episodes. If you were on campus, you would have 24 hour and 20-minute lectures. And so I feel like I would be cutting you shortchanging you if we didn't have 24 episodes, as you would normally expect. Now you're probably sitting there worried, like, oh no, we're going to have an extra week of lectures which we're going to be responsible for. That's not my intention. So today does mark the end of the official covered material. So there will be no material after today that you are responsible for. However, I would like to give you 2 bonus episodes next week at the regularly scheduled time, so Tuesday and Thursday at 9:30 in the morning. And we're going to use those particular episodes to discuss some other operating systems topics. So they'll kind of be a bit shorter, maybe a bit more fun, but not material that you need to know for your final assessment. Now, I haven't pinned down the exact topics, so I don't want to come out and say, oh, we're going to talk about X and Y, but one of the things we are going to talk about next week is going to be networking, in particular how it integrates with your operating system. Obviously, if you've been to the course website in any previous term, networking actually used to be a part of the course, but it wasn't that it was removed so much as it was we had more content that we could reasonably cover in a live lecture. Because of course you've got midterm review and final exam review sessions, and it just never worked out that we got to that section of the course. And we're not talking about, once in a blue moon we didn't get to that section of the course. We never got to that course. In years, we never managed to get there. But because of the unique format that we actually have space for this. So next week I will talk a bit about networking and some other really fun stuff related to operating systems. It's your choice whether you watch the videos. Maybe you're interested, maybe you're not. That's up to you. But if you are looking for more, there will be more next week. And if you are done with the course, then don't worry about it. After today, you'll be officially done all of the coverable material. So, what we should be aiming in these online courses is not to give you the minimum, the bare set of what we have to cover. We should be working towards giving you the best possible experience that we can. So I don't want to shortchange you on that. All right, with that noted, our operating system of the day, it's not Linux. Our OS of the day is actually 2 OSs of the day. It's both Android and iOS. And if you're wondering, yes, I will continue the OS of the day next week as well. So our OSs of the day are the cell operating systems that most of you are familiar with. Now, these 2 operating systems were actually released fairly close to each other. And they have a lot of similarities. So Android actually wasn't originally a Google product. It wasn't a Google creation. It was actually started back in 2003 as a fork of the Linux kernel. And Google actually bought the company that was working on it. And really, Android is just a fork of Linux. And while it may not be completely compatible with all Linux applications, it's usually pretty straightforward to actually run standard Linux code, or at least get it to work within Android. Now, they have made a number of changes to this particular fork, specifically because running on a cell phone is obviously quite different than running on a desktop, which has a constant power source. For example, if you think about a cell phone, you have a very limited battery life. And you want to make sure that your user can use your cell phone for a minimum of 8 hours between charges. I mean, that would be the ideal thing. So what can you do as part of the operating system to improve the battery life? And there's a number of things that you can do. And one of the ones that Android actually does is that they have optimized how processes are managed. So think back to that section of the course where we were looking at system calls, and think about if you want to fork a new process and you close a program, how much work is actually involved there. So when you create a new process, you've got to create the new process structure, you've got to create the new address space, you've got to copy the contents over, you've load the program into it, and then you're going to have to, set up parent-child relationships and PIDs. It's a lot of work to create a new process. Whether you're doing that by exec-v or fork, it doesn't matter. It's a lot of work. And then when you're destroying a process, there's also a lot of work that has to be done because you've got to destroy the address space. You've got to notify your parent that you've terminated, and so on and so forth. And one of the things that's interesting about using a cell phone, and please keep in mind, I'm not a texter. I use my cell phone for maps. I don't really use it for much. But most people are opening and closing the same app repeatedly. So whether that's Tinder or Grindr or your text messaging service, which I don't even know what that app is called because I don't use it. It doesn't matter. Maybe it's Facebook Messenger. You're going to open, or Snapchat or TikTok. Is that even on a cell phone? I don't know. So you're going to open that app. You're going to do something in it very, very quickly, send a message, and then you close the app again right away. So if you think about the burden from the kernel's perspective of constantly having to create this process and then destroy this process, it's actually a lot of work. So what Android is doing is it's not actually destroying the process when you close the app. It actually keeps the process around as long as it can. And then the idea is, because of that constantly opening and closing the same subset of programs, the next time you open it, it doesn't actually have to go through the whole method of creating a new process and loading the address space because it's still there. Now, of course, this is going to run you into some problems with respect to the amount of limited resources there are in the system. So periodically, you're going to actually have to kill some of those processes truly and kill the oldest one, kill the one that's least frequently used. There's many different cache eviction strategies we could use here to actually choose which processes to actually destroy. Now, there is some discussion of maybe rejoining a lot of these Android ideas back to the mainline Linux kernel. I don't know if that will happen. So that's just some brief comments about Android. Then you have iOS. Now, iOS is also kind of, I want to say, a fork of Mac OS X, except unlike Android, where things are reasonably easy to transport between like Linux and Android, the applications on Mac OS X are very much incompatible with iOS, even though they actually share a large body of code. Some of the other things too is that while Android gets a lot of its concurrency and those elements from Linux, and it's actually kept a lot of those, even if it's modified how they work, iOS has taken a different approach. So they didn't give users the concept of multitasking until significantly later in the lifespan of the operating system. So up until about the iPhone 3GS, they had almost no multitasking. So if you were listening to music, you couldn't also be surfing the web. If you were on a phone call, you couldn't be updating at the same time. And I want to say this, for the most part, kind of makes sense, because if you look at the size of the 3GS and those older cell phones, they're actually quite small. And I'm not really, and the processing power, I don't know how you would have really provided a good user experience. Or why would a user be trying to play a game and listen to music at the same time? Because the game has music. I kind of get where they're coming from. Now, it was actually possible to jailbreak the phone and actually get multitasking turned on, so actually allow those things to happen. But of course, you've got to jailbreak your phone to do that. And then some of the other things is that they decided to gradually bring in support for multitasking. So still we don't have a full level of concurrency that you would expect. But you can now do background downloads and play music at the same time. You can do updates, and there's this concept of suspension. So they have been improving what they support, and certainly with things like the iPad Pro, which has more power, more screen space, they realize that yes, you will need to do multiple things at the same time. But the level of support for this is not the same as it is in Android. And I actually understand why they would choose to do that. You have to look at how the device is actually used. Is this device going to be used to run 1,000 programs concurrently? Why would you, like on a 4-inch screen, why would you do that? I don't think many people do. I mean, don't get me wrong. I've seen some crazy people do some crazy things on cell phones. I have seen people like write code in a VI window on a cell phone, and that was probably one of the weirdest things I've ever seen. Sorry if you're one of the people that do that. It's just I suck at typing on the screen, so I can't even imagine writing code in VI on a tiny cell phone screen. All right. So, yeah, and if I don't sound like I'm much of a cell phone person, I'm not. I did get a cell phone. I want to say it was 2010 or 2011, for the purposes of having a map in Vancouver. Prior to that, and we did have a second phone, and it was what's known as a John's phone, which is the most basic kind of cell phone that exists. It's literally just a box, and it has the number pad on it. I think it's actually meant for senior citizens. And so you can only dial. There's no texting. It doesn't have an address book, so to speak. I mean, it does, but it's a door on the back of the phone, and there's a little paper book and a pen, and that's where you store the phone numbers. Yeah. Not a big cell phone fan. All right. So what I'd like to do now is go back and look at the 2 sample problems that I introduced in our last episode. So the first one was path trans. Now, these are fairly involved, so I'm not going to have the problem up on the screen at the same time. So if you're following along with the episode live, or if you're following along at some other time, open up pathtrans.pdf, and that's the first sample problem we're going to do. But what we've essentially been asked to do here is we want you to write the code to take a path and retrieve the I number using this body of functions that have been provided to you to do the different lookups. Now, there's many different ways that you could actually approach this problem, and I just want to show you one possibility for it. So I'm going to open up OneNote here, and I'll try to write as neatly as I can. Sorry, Twitch comment. But writing code on a cell phone using Seashell is fun. There are so many things that are wrong with that. I don't even know where to begin. All right. So let's start then with path translate. So let's just call this, and I'm going to short form a lot of the names of things here just because I don't like writing too much. It takes too long. So we're going to call this function translate. And it's going to return an integer, and that integer is going to either be the I number, or it's going to be the error code if we were actually unable to find the I number for the path that was given. So I'm going to set an initial I number. You know, it would probably be a lot more easier if I actually wrote this in VI. Oh, well. So we've got this I number, and we'll set it equal to 0 to start with. So this is our initial I number. And we're going to make the assumption that the I number of root is 0. Traditionally speaking, the I number of root is not 0. It's actually usually something like 2. And the reason for that is we often need to keep track of which blocks on our disk are bad. Now, what a bad block is it means there's some kind of damage to the magnetic material such that we're not really able to read or write from that block very well. And we have to keep track of those blocks so that we don't actually use them when we're dishing out blocks to everybody else. So our root actually doesn't usually start at 0, but for today it's going to. All right, now we're going to have a for loop. And it's going to be, this is pseudocode, by the way. So I is going to be from 1 to the number of components in our path. So if you're looking at a path as something like there's a number of components here. You've got, right? You've got things like user, bin, bar. So from I equals 1 to the number of components, we're going to first check, oh, root, by the way, is also a component. We're going to check if the first thing in our path is a directory. So we've got our initial I number set to 0, which is corresponding to the root. Or at least this is what it should be. So I'm going to make sure that my I number corresponds to a directory, because you can't search inside of something that isn't a directory. So I'm going to say if we are not a directory, then what we're going to do is return invalid. So that would probably be like a negative integer. So we're simply saying we are going to search for our component inside of a directory, but if our current component, that is our current I number, doesn't correspond to a directory, then we couldn't search for an I number inside of it. So if it's not a directory, this is not a valid path, so we're going to actually have to return an error code here. Now, at this point, we know that we have a directory, and so we are going to get the I number of the next component of our file name. So we are going to do the D search. Now this here is component 0. So we're going to do D search, and you'll note that we are looping from 1. So we start here. That's where we're starting to look. So we're going to search for the next component, which is number 1 here. We're going to search for its I number in the current directory. Now, what's going to happen is if this user exists in the root directory, then dsearch is going to return to us the I number of the root directory. Oh, hello, spider. There's a spider. Sorry, Zelda book, but you're going to be used to kill spiders today. All right. Sorry about that. The problem is little teeny spiders grow up to be great big spiders. And while I'm not particularly afraid of spiders, I don't really want them crawling around on my desk either. All right. So if dsearch succeeds and we find the next component, then I number will correspond to that component. If, however, dsearch fails, then the I number that will be returned will be less than 0, because no I number should be negative. So we need to test whether inum that is returned is less than 0. So if inum is less than 0, then we're also going to return invalid. Comment on Twitch is making reference to how many spiders Link has killed. Yes, he has indeed killed a lot of spiders. Though apparently not in Breath of the Wild. Maybe in the sequel. Cross our fingers. All right. So if inum is less than 0, then we want to return invalid as well, because this path wouldn't be valid there either. Otherwise, the I number corresponds to an actual thing, and we can continue the search. So why this works is that when we reach the end of the path, we won't have any more path components, so we'll stop looping. And we have either found the item and its I number, or we haven't found the I number, and we return invalid right away. So this is just one way. There are many possible solutions to this particular problem. All right, so this problem's not too bad, I find. But then we introduced a second problem. And you know what? Let's make a new page. All right. So the last sample problem of the course is probably my most favorite sample problem. I'm not going to lie. It is file I/O. So if you're following along, file I/O is the problem we're looking at now. And what we have is 4 simple lines of code, and we're making the assumption that we are going to be reading and writing from a very large file, much larger than whatever region we are trying to read and write from. So we are reading from a valid part of the file, and we are overwriting a valid part of the file. So we're not adding any new data to this particular file. We're also going to assume that we have already opened the file, so we already have its I number, our tables are already completed in the process, but we're going to make the assumption that any block or inode caches that we have are empty. So what we want to know is, based on these 3 file operations right here, seek, write, and read, how many reads and writes to the disk happen for write, and how many reads and writes to the disk happen for read, and for each of them, how many cache operations actually happen. So this is kind of a fun problem. I personally really like this one. I don't think everybody likes it, but I do. So let's go over here. So the first thing that we need to do is, and I'll write the name of this one up here, this is file AO. So before we can figure out how many reads and writes are going to happen for each of these different operations, let's go back to file AO here. There it is. Before we can figure out how many disk reads and writes happen, we need to figure out how is this file actually stored on the physical disk, because we need to know information like how much data can we access via direct pointer? How much data are we accessing by the single indirect pointers? We can't figure out the number of disk I/O operations if we don't know that information first. So what we're going to do is first compute the information about the disk itself. So let's go back over here to OneNote, and I'll write these things down. So first off, we know that our block size is going to actually be much smaller. So if you're looking here, we'd usually use a block size of 4 kilobytes, but actually here we have a 1 kilobyte block size. So our block size is going to be 1024 bytes, which is also known as 1 kilobyte, or 2 to the power of 10. Great. All right. We also know that our pointer size is equal to 4 bytes, which is fairly standard. So that means the number of pointers in a block is going to be 2 to the power of 8. And I arrived at that because I took 2 to the power 10, which is the block size, and I divided it by the pointer size. Now I want to know how much memory is actually accessible from each of these pointers. So in our file, our inode, we notice that we have 9 direct pointers. Some real good spelling. 9 direct pointers. So with 9 direct pointers, we can access 9 times 1024. So that's 9 kilobytes. Now, it's going to be very useful here to actually keep track of what range of bytes this is actually accessing. So I'm actually going to draw this in a different color. So this is giving us access to bytes 0 to 9 to 1 6. Not too bad. All right. Now, going back to the problem here, we make note that that's not good enough. We can't stop there because our lseek operation is advancing the pointer in the file to byte 10,500. So what that's telling me is that these direct pointers, while I am aware they exist, my reads and writes aren't happening through the direct pointers. So now I need to figure out, are they happening from the single indirect or the double indirect? So we have one single indirect pointer in the inode. And that's going to let me access 1 times 2 to the 8 times 2 to the 10 bytes of memory. So what you're looking at here is we are looking at 256 kilobytes. Because we have 256 times 1 kilobyte, 256 kilobytes. And if we look at the byte range here, which was actually what's more interesting, we see that the range of bytes is actually going to be from 9 to 16 to a very big number. And you can compute that as 1024. Let's see, where's our calculator here? It is. So we've got 256, and let's multiply that by 1024, and let's add 9216. So you're looking at going to byte 271,360. Okay. Now we could continue to evaluate our file inode here and look at the double indirect pointer, but I honestly don't see a point, because if we're looking at the problem, we are starting our reads at, or our write at byte 10,500, and the write is 1,000 bytes long, which means that it's finishing well within the range of bytes accessible via the single indirect pointer. And then the subsequent read, which would happen starting at byte 11,500, ends at 12,500, which also falls well within the single indirect block. So there's no point in looking at the double indirect pointer here. So now that we have this kind of laid out, now we need to actually look at, we know that our read and write are going to happen via the single indirect pointer, but is the read going to, the read of 1,000 bytes, 1,000 bytes is smaller than our block, but is the read going to be inside a single block, or is that read going to be spread between two blocks? So now we need to take a closer look at how the memory is actually laid out within the block. So let's suppose we have our inode here, and the inode has the single indirect pointer to a block of pointers. Now, in this block of pointers, make sure I give myself lots of space, I know that the first pointer is going to be starting at byte 9216. So this pointer here is going to point to bytes 9216 of the file. This is a bad way of drawing it. Let's draw this a different way. So our first single indirect pointer right here That's a better block and pointer diagram, right? This is going to point to bytes 9 to 16 to 10,240. And then I look at the next pointer in my single indirect block. It's going to point to a data block that contains bytes 10,240 to 11,264. And then we keep going with this pattern, just like this. And so this is going to be bytes 11,264 to 12,288. And then this one is going to be 12,288 to 13,312. And that's as much space as we need. Okay. Now I know that my write starts at 10,500 and it ends at 11,500. So I need to identify which of these file data blocks does it start and end at. And looking at these ranges here, this is why you should draw these ranges, is because then you can figure out exactly where this write starts and ends. I see that my write starts here and my write ends here. So this is my write operation. Okay. Now that I know that, I can now compute how many reads and writes are actually going to happen in order to perform this write. So let's do this in red right down here. So my write, we are going to read the inode because we are assuming that it's not in the cache, and I'm going to put it in the cache here. Then I am going to read the single indirect pointer block. And I'm going to put it in cache as well. And then I am going to read the first data block. Put it in cache. And then I'm going to read the second data block because now you might be wondering, why am I reading these two blocks? I'll get to that in a minute. I'm going to read the second data block. Now, I have to read these blocks, but I'm not reading them. I'm supposed to be writing to them. But the reason why I had to read the data blocks first is because you can't do a partial block write. And if you look at where this write happens, it happens halfway through the beginning of this block and it ends halfway through the end through this block, which means I'm doing partial updates to both of those blocks. So I have to read them before I can write them. Then what I'm going to do is I'm going to write the first block. I'm going to write the second block. And then the one that always surprises people is I have to write the inode. So we have 4 disk reads and 3, that's some good spelling, disk writes, just to do that write operation. Now, if you're sitting there wondering, why didn't I address the seek? That's because the seek actually doesn't do anything to the disk. All of the seek is going to do is move the file pointer in the file descriptor table for the process from 0 to 10,500. Okay, so this is my write operation. Now let's go back and look at the read operation. The read operation happens right after the write, so it's going to happen starting at byte 11,500, which is the new position of the file. So we are going to start our read here, and we're going to end at 1,000 bytes later, which falls into the next block here. So this is going to be our read operation. Now, for the read of 1,000 bytes, we already have most of the data in our cache. So the inode's in the cache, the block of pointers is in the cache, and the second data block is in the cache. So all of those things we don't have to do I/O ops for. We still have to get them from the cache, but it's significantly faster. However, our read ends in this third block down here. So we are going to have to read a third data block. And since we accessed file data, I have to write the inode. You'll notice I haven't enumerated all the other operations, and that's because they were all cache operations, not disk I/O. So I am only listing the disk I/O operations here. It's not that the other reads and writes don't happen, it's just that they're happening from the cache. So in this case, we have one disk read. That's why I'm writing disk read, and we have one disk write. We're writing the inode, remember, to update the last file access time. What this little problem should point out to you, though, is that making use of a cache is very important for secondary storage, because you go from having 7 disk IOs to 2. This can really improve things. All right, so with that, that is the 2 sample problems to end up the file system section of the course. What I'd like to do now is move on to the very final topic, which is very short. So if you're sitting there worried that we have not that much time to cover something, don't worry. So the last thing that I want to talk about is virtual machines. Now, this is a topic that's fairly new to the course. We wanted something that kind of wrapped up all of the things that you've learned and kind of connected to some modern operating systems ideas. So virtual machines, this concept has actually been around for a really long time. And what a virtual machine is, it's a simulated or an emulated computer. So for example, Sys161 is an emulated MIPS R3000. So in a way, Sys161 is actually a very simplistic virtual machine. It is a fake computer. And there are many different virtual machines out there. For example, if you look at latest versions of Windows, where they actually let you run a Windows application in a different version of Windows, even though you're using Windows 10, you can run a program as if it was Windows 95. Well, that's because it has a virtual machine, a virtual computer set up, an emulated computer that will let that code run in the way that it expects to do so. And we've used this this concept is not new. We had this concept of virtual machines back in the 1960s, but unfortunately, due to computer performance, this wasn't really feasible. And while people continued to toy with the idea, the true power of VMs weren't really realized until probably around 2005. And the only reason why VMs kind of made this resurgence in 2005 is because hardware support was needed to make the performance of virtual machines acceptable to users, and we didn't get that until the early 2000s. Now, of course, there is a lot of hardware support for virtual machines, and so VMs actually run quite well. It's still not as fast as running an OS on bare metal, but we can do pretty good. So why do we have these virtual machines? Why do we use them? Well, one of the reasons why we might do them, such as in this course, is we want to be able to create an operating system for a different system. So we want one machine to behave like another machine so that we can actually create tools for some other computer. And you've probably done this if you've ever done any iOS development. Xcode has a simulator for iOS devices built in. So you are causing your Mac computer or whatever computer you're using to behave like a cell phone so that you can actually run and test applications for that cell phone without actually having to do it on the physical hardware. And there's a number of reasons why you may not want to do it on the physical hardware. Maybe you don't have it. I don't have an iPhone. Maybe you can't afford it right now. Maybe you're concerned about you're not ready to run on the bare metal yet. Maybe there's some bugs that might be particularly harmful. There may be many, many different reasons why you don't want to do your experiments on bare metal. But we also use virtual machines for isolation. So for example, let's suppose that you really, really want to run Nuke, which is a video editing tool, and it's quite expensive. So let's suppose you want to run this, or maybe you want to run AutoTune, which is an audio editing tool. It's also very expensive. So let's suppose you can't afford it and you go on BitTorrent and you acquire a copy of it, and you're sitting there and you're like, well, I just downloaded this really expensive software from BitTorrent. I have to run all this crazy cracking stuff, and I don't know if any of this is injected with viruses or malware. So you're really concerned about actually installing these tools on your host operating system. Well, this is what a virtual machine is meant for. You can create a machine inside of another machine that is isolated from the actual bare metal. It's isolated from the host operating system. So you install your virtual machine, you've got a separate copy of Windows or Linux running, and then you install your downloaded, your pirated software there. And then if there is a virus, it stays contained to the VM, which you can just pooch like that. And if there's no virus, then you can install it on your bare metal system or your host OS. So this idea of a virtual machine is a powerful tool for developing software for other devices. It's also really powerful for isolation. And that's one of the actual really big goals of virtual machines, is you want to make sure that the virtualized hardware and the virtualized operating systems are isolated from the host OS and the bare metal. You don't want these two operating systems to know about each other. You want them to be isolated. You want to make sure that behavior inside of the virtual machine is as if it was running on bare metal. You don't want the guest operating system to believe that it's not the only one. So what I mean by that is you don't want to have to make any modifications, add patches or drivers or things to it. Okay. So just an overview of some things that we need to talk about here is to review what actually happens in your computer. So you have a number of, when we say bare metal, we're saying the actual physical hardware. So that's things like your CPU, RAM, and the actual physical devices. That's the bare metal. And the CPU is going to actually execute the instructions of both the operating system and the user programs. The CPU often has different modes of privilege, one for executing kernel code, which is privilege, and that's actually a CPU setting. And then when the user programs are running, they'll run in unprivileged mode. And that way, if a user program tries to run a privileged instruction or translate a privileged address, we'll get an exception. And all of the kernel of their operating system pretty much handles everything else. The computer really just executes the instructions. So your operating system kernel is responsible, of course, for handling the interrupts and exceptions raised by the CPU. So interrupts, devices that need attention, somebody pushed a key, a network packet arrived, timer's expired, the printer is now free. All of those things are hardware interrupts. And then exceptions are things like software. So that's the system calls, illegal instructions, like you don't have the correct permissions. That's going to be division by zero and so on and so forth. The kernel of the operating system is going to handle all interrupts and all exceptions. So the CPU has to be able to execute the kernel's exception and interrupt handler when one of those is received by the CPU. And then, of course, the kernel of the operating system is responsible for creating the execution environments for programs, that is, creating file descriptor tables, managing memory, loading address spaces, all of that, and managing concurrency, synchronization. All of those things are done by the kernel of the operating system. And when we're talking about virtualization, we have to go back and think about these roles, because we're going to run into a few problems when we have an OS running inside of a fake computer, inside of a host operating system on real hardware. So let's look at a very initial attempt to create a virtual machine. And I'm kind of picking on CS161 here because it's kind of the simplest one to think of. So you create a virtual CPU, and how you create a virtual CPU is almost like an assembler or a compiler, I want to say. So the virtual CPU is going to receive a binary program written in the assembly language of that virtual machine. So sys161 receives binary programs written in the MIPS assembly language. And what that actually does, that sys161 virtual machine, is it takes those MIPS instructions and it translates those instructions to x86-64. Well, x86. So we are going to capture all of the instructions for the virtual CPU and translate them into instructions for the host CPU, the bare metal. And then our operating system will run on the virtual CPU. But this actually raises some really interesting problems. How do you do interrupts? So if I push a key on my keyboard, how am I gonna, and that's meant for OS 161, how do I make sure that gets forwarded all the way forward? What about exceptions? What if the guest operating system is running a user program and that user program is trying to access privileged code? What happens? How do we detect the exception? How do we handle these exceptions, and so on and so forth? And then we have this concept of privilege. How are we going to actually distinguish between the guest operating system doing something bad, the user program doing something bad? Well, the guest operating system is actually running as a user program on top of the host operating system. So there's all these different privilege issues. Then we've got issues of virtual memory, how you actually handle memory for these systems. There's many complications. Now, I'm really only going to go over this at a very, very high level, just to give you a taste of a more recent research area in operating systems. So first off, let's look at interrupts and privilege. And I want to take you back in time to actually looking at, I feel like I've skipped a slide. I haven't. Okay. So I want to take you back in time to looking at interrupts and privileges from the perspective of spin lock acquire. So you may remember when we talked about spin lock acquire that I mentioned that in order to reduce spinning from threads that are trying to acquire the spin lock that is already owned, we disable interrupts. And that means that that particular core, no other thread could actually run, which means that you will own the spin lock and there will be no spinning on that core. So in spin lock acquire, I'm going to disable interrupts. But if I'm spin lock acquire in the guest operating system and I'm trying to disable interrupts on my virtual CPU, do I also need to disable interrupts on the physical CPU so that interrupts that are actually received by bare metal don't end up getting forwarded through to my virtual CPU? Because that doesn't seem like a good idea to me. Because if I'm the host operating system, I don't want one of my user programs to somehow be able to disable interrupts in the back end. Because maybe I'm disabling interrupts incorrectly in the host operating system or the guest operating system. Maybe I don't want the guest operating system to do damage to the host. So we don't really want the VM to disable interrupts on the actual bare metal. So how do you handle that? And as I said before, when you have interrupts, how do you handle forwarding those interrupts to actual computers? And we'll talk about VM in a little greater detail in a minute. So these are just some things to think about. So you know how it works when you've just got one OS running on hardware. But now you've got one OS running on fake hardware, running in another OS, running on real hardware. All of a sudden, some of these things that we take for granted start to become really complicated. And before we can really address how any of these would be solved, we have to look at something called a hypervisor. So a hypervisor is the virtual machine manager, because you can actually have multiple virtual machines. And in fact, if you're looking at something like Amazon's AWS, you can, they don't have every possible machine sitting in every data center, and you're not actually running on that particular machine you set up. What you're creating is a virtual machine on their servers. So their hypervisor is actually managing multiple virtual machines simultaneously for users around the globe. So the hypervisor's job is to create and manage the virtual machines themselves. And there are two big categories of these. Type 1 hypervisor, which someone here on Twitch is commenting on the Type 1 hypervisors, which run on bare metal. There is a website, it's qubes-os.org, and if you want to post that to Piazza, by all means, please do. So there's Type 1 hypervisors run on the bare metal. You could almost think of a Type 1 hypervisor as almost being a kind of operating system in itself, but not one that a user interacts with. So if you look at this diagram here, you've got the Type 1 hypervisor running directly on the hardware, and then all of the virtual machines run on the Type 1 hypervisors. And this is probably how Amazon's AWS model is actually set up. This is actually going to, by the way, give you the best performance because there are fewer layers between the guest operating systems and the actual metal. Then we have the Type 2 hypervisor, which is what you have the most experience with and what most consumers have seen. And that is, it's a hypervisor that runs as a user program on a host operating system. So your host operating system, in my case here, I'm running on Mac. So I've got Catalina, and that's running on my CPU. And then if I install VirtualBox or VMware, that's a Type 2 hypervisor that runs as a user program on my host OS. And then my virtual machines run through that. And how we solve some of these issues that we briefly talked about a minute ago really depends on whether you're using a Type 1 hypervisor or a Type 2 hypervisor. So this is just an overview of those two kinds of hypervisors. But how do you handle privilege between these two hypervisors? So Type 1 hypervisors, because they are running in on the bare metal, they are actually a kind of operating system kernel in themselves. So they actually run in privileged mode, which means the VMs are running in a less privileged mode. And they shouldn't be able to disable interrupts on the bare metal. So what's going to happen is any kind of unprivileged instruction that should be forwarded directly to the hardware. So if your VM in a Type 1 hypervisor is running like add is just going to be executed normally on the host, the bare metal. But when we have a privileged instruction, we actually need to trap to the hypervisor, and the hypervisor needs to be able to handle what's happening with privileged instructions. So it needs to be able to figure out, is this privileged instruction request coming from the guest operating system? Is this coming from the kernel, meaning this is something I probably want to permit? Or is this the user program trying to nefariously execute a privileged instruction? In which case the hypervisor doesn't want to forward that to the host or the main hardware, and it wants to actually throw an exception directly back to the VM without even involving the bare metal. So yeah, there's going to be interesting issues with how does a Type 1 hypervisor handle privilege. Now, Type 2 hypervisors are interesting because they are running in unprivileged mode. And if you have unprivileged instructions running in an unprivileged mode, you can just translate and execute as a normal user program, no problem. But if you have the user program on a guest OS running in a Type 2 hypervisor, and the user program is executing a privileged instruction, then the hypervisor has to be able to simulate the behavior of privileged instructions. So it needs to be able to figure out, was this the kernel of the OS making this. So the hypervisor here has to be aware of whether the VM is actually running in a privileged state or an unprivileged state. But since it's all user programs, this should be fairly straightforward. And so the hypervisor will be like, okay, I have a privileged instruction request, and the kernel everything is operating in privileged mode here. Oh, and this is something I can forward. And so what's going to happen is when you have an appropriate privileged request, then the type 2 hypervisor will simulate the behavior by making system calls in the host OS. So if we're trying to write to a file in the guest operating system, and that is a totally valid thing, so we're in the system call for writing to a file in the guest OS, and that's going to cause some privileged code to run, and I need to write to the file. Well, the VM can't write to the file because it's a user program and it doesn't have access to the privileged instructions of the host program. So the hypervisor will capture that behavior, notice that it's valid behavior, and then translate that to the appropriate system calls for the host operating system. And as you can see from that, obviously type 2 hypervisors are a lot slower than type 1s. Lots of translation going on. So how do the type 1 hypervisors handle privilege then? So it seems fairly straightforward how a type 2 would do it because it's user programs and you've got to translate the instructions anyways, so it can just capture things and keep track of virtual CPU states. But with a type 1 hypervisor, we generally, we don't, we can still trap a privileged instruction, but it's much harder for the hypervisor here to differentiate between this is the OS making a privileged request or this is the user program making a nefarious privileged request. And so how a type 1 hypervisor has actually solved this is by making use of more of the privilege levels of your CPU. So your CPU doesn't just have privilege and no privilege. It actually has 4 levels of privilege. And we typically use the full on and full off. But there's 2 in the middle. Why don't we use those? And that's exactly what the type 1 hypervisor does. So it actually makes use of rings. So the hypervisor itself runs in the highest privilege mode. The guest operating system runs in the next highest mode. And then the user programs on the guest operating system run in the lowest privileged mode. And that way, we've got levels of privilege. So we can set the privilege mode on the CPU. And if the guest operating system, let's say we've got a user program and that's running, then we can have the CPU in the lowest privilege mode. And if they try to make a privileged request, we'll know it's bad and we'll be able to respond appropriately. But if we're running kernel code for our guest operating system and they make a privileged request, we'll be able to say, okay, well, it's not as much privilege as the hypervisor, which should be allowed to do things that the guest OS can't, but we still know this is something we should probably either capture and translate or deal with appropriately. So that's how type 1 handles it. And that ability to have multiple rings does exist in your CPU. Doesn't mean we're using them, but. So another thing to talk about, and this is going to be with respect to type 1 hypervisors. I feel like type 2 hypervisors are actually fairly straightforward. But type 1 hypervisors, how do you deal with memory? So you want to create this environment where you've got multiple operating systems running on one computer at a time and multiple users using each of those. And one way that you could divide up the physical memory is to say, okay, VM1, you get the first 2 gigabytes, VM2, you get the next 2 gigabytes, VM3, you get the next 2 gigabytes. That's actually fairly straightforward, but there's some problems with that particular way of dividing the memory on the system. And the problem is that maybe you're running Windows 3.1. I don't need 2 gigabytes of RAM for Windows. Windows 3.1 can't even handle 2 gigs of RAM because it uses 16-bit addressing. So we actually end up with this problem of if we do kind of this, you get a chunk and you get a chunk and you get a chunk. Yes, it's isolated, but we end up with problems of fragmentation and reducing the total number of VMs that we can actually run at the system simultaneously. So what we really want to support is something like paging. So most of the operating systems use paging by default. So we also want to do paging of this. So each OS gets exactly the amount of memory it actually needs, so we can actually run more at a time instead of doling it out. But here's the problem. If we give each operating system the ability to do paging, we want them to believe that they have full access to RAM. But if we're giving them full access to physical memory and we have two OSs running at the same time and they're not aware of each other and we don't want them to be aware of each other, then there's the possibility of collisions. So they could both map to the same physical page. So how do we handle this problem? So how we actually handle this problem is the hypervisor actually needs to do the memory management on behalf of the guest operating systems. So we actually introduce another level of page tables called the shadow page table or extended page table. And the idea here is the hypervisor is going to present physical memory to the user, the guest operating systems, as virtual addresses. And so the guest operating system believes it has access to full everything in physical memory, but it doesn't. And since it's virtualized, it's abstracted by the hypervisor, the guest OS will be none the wiser. But now we have this problem of every address translation actually has to go through the hypervisor. So we're going to go through the kernel of the operating system is going to send the instructions out. And then it's going to have to go to the hypervisor. The hypervisor is going to have to perform a translation using its shadow page table. And then it can send it to the MMU to do the actual translation. So you've got all these levels. That's going to be really, really slow. So what we really need to do is make our MMUs aware of the shadow page table. And this is another one of those hardware optimizations that we actually are relying on now for virtual machines to work efficiently. So instead of having all of the virtual addresses from the guest operating system have to be translated by both the hypervisor and the CPU, we now want to just be able to do this directly in hardware. So we don't want hypervisor to be involved unless it has to be. So modern CPUs, and I'm considering that the Nehalem architecture and up, so that's the first generation of Core i7s, their MMUs support extended page tables. So that means that the MMU actually knows about the hypervisor's shadow page table. And so when we are we're doing a memory translation for one of the guest operating systems, it can actually look at this and say, okay, well, right now I am running guest OS 7. So I need to look up shadow page table 7 to translate this, and then I can use these other page tables to finish the translation. So we now have this additional level in our table. And what's interesting is now we have, instead, you know that when there's a context switch on the MMU, you have to change the page table pointer to point to the new process's page table. Well, now the MMU has to do what's known as a world swap. So the extended page tables, the pointer to the shadow page table, when we are swapping between doing translations from one VM to another VM, we have to update that shadow page table register. So the hypervisor is going to still be involved, just not on every translation. So the hypervisor would be involved on faults, and the hypervisor would be involved whenever there's a world swap. And management, of course, but not on successful translations. So that's improving our performance there. So that's a fun thing. Then we have to discuss, shadow page tables sound like an RPG item. Yes, I suppose it does. Twitch comment. So how do we handle I/O and devices? Because we know that we're going to need to have things like secondary storage devices. We're going to need to be able to talk to keyboards and mice and network cards. How do we do that? So one of the interesting things is doing the disk stuff. So for guest operating systems in a type 2 hypervisor, how it actually usually happens is your disk is actually just a file. So we'll create like a 16 gigabyte file, and that will actually be treated as a disk. Really, it's just a file. But the VM will actually kind of write to it using a certain kind of file system, even though at the end of the day, it's just the commands for writing get translated to system calls in the host operating system. So it's actually quite common to see secondary storage just be created as files in the host. Another way that you could do it is if you were running on the bare metal, you might give each disk a partition. So you might actually physically partition the disk and give a partition to each of the VMs. That doesn't make as much sense, especially if you're something like Amazon AWS, because you don't want to be partitioning your disk so often. So actually taking the approach of having the hypervisor present the file, the disk as a file, is actually a lot of sense, because you can create and destroy files very, very easily. So that's one way that we can handle secondary storage. But how do you actually handle things like keyboards? So there are different approaches. There's this concept of device pass-through. So we may want certain devices to only be attached to certain VMs. For example, maybe I have 2 keyboards plugged into my computer, and maybe I want to make sure that keyboard 1 only goes to VM1 and keyboard 2 only goes to VM2. So that's device pass-through. So we can actually map devices to particular VMs. And the hypervisor would have to know that, hey, interrupts, it would have to be able to capture the interrupt and say, okay, this interrupt is coming from this device, and this device is mapped to this VM. And so when it receives that interrupt, when it handles that interrupt, it will pass it through to that particular host VM. We also want to make sure that devices are kind of isolated with the VMs. So if I have assigned a device to a particular VM, let's say that I've assigned my one and only keyboard to VM number 2, or VM number 1, and VM 2 is sleeping, but I don't want key presses to also be passed to VM 2. I don't want those key presses to actually be able to wake up the sleeping VMs. So we want to, in some cases, make sure that we are isolating interrupts from VMs that don't want them. Now, in order to do this, we need hardware support. And again, this is why VMs haven't really done this virtualization until the last 15 years, is because we've been waiting for hardware to be at a state where we can actually put VM support right on it, which we have really great now. So it's a really brief taste, I want to say, of how a VM works and what different problems are associated with implementing hypervisors in VMs. It's just a teeny taste, because we just wanted to show you what else is out there. Certainly, if you want to read more about it, the textbooks are great. They can talk about that in greater detail. Go work at VMware, and they hire co-op students. But let's just kind of finish off by saying, why are we using these again? So, as I kind of mentioned at the beginning, one of the reasons why we use VMs is to provide isolation. So it creates a really safe, isolated sandbox. So whether you, and this is something that Amazon and Google, they're using VMs to create sandbox environments for users. So we want to be able to test and develop programs for other architectures without actually having that physically in front of you, and we want to be able to run sensitive or suspect applications. Or maybe you want to have fun. So for me, I once kept a Windows 3.1 VM around because I liked Windows 3.1 games. You can't install Windows 3.1 and expect it to run on like an Intel i9. That seems kind of silly. So this does provide you a nice sandbox environment. But two of the other things that we haven't really talked about is how virtualization can improve resource utilization. So if you look at places like Amazon, before AWS existed, if you look at how busy their servers were throughout the year, it wasn't uniform. So there were periods of the year where their servers were being just super, super busy. And that makes sense. So right around the Christmas season, it gets really busy because everybody's going online and trying to buy presents. And so in order to support traffic during the holiday season, they actually had to purchase extra servers. But then in the downtime, in the summer months, those extra servers they purchased in order to support, the Christmas traffic, the holiday traffic, to idle. So they thought to themselves, how could we, number one, make our money back and utilize these resources? How can we make more money and utilize the resources that we have? Now, they couldn't exactly create a summer holiday that's as big as, the winter holidays, but they realized that through virtualization, they could create VMs for users on these servers during their downtime and rent the time out. So it's like you can get for like 7 cents an hour, you can have a VM on Amazon. And that's a great idea. So you can actually, instead of you purchasing the hardware and maintaining the hardware, you can, for so many cents an hour, have Amazon buy the hardware, maintain the hardware, and all you got to do is use it. So it's great for users and small companies because they don't have to invest in the resources and the manpower. And it's great for Amazon because they're using their resources better and they're, of course, making more money. So it's kind of a good thing. And I've used Amazon AWS a fair bit. It's pretty neat. If you're interested, they actually have a free tier. I think you get 750 hours free per year. It's pretty low-powered VM, but yeah. It's pretty good. And of course, Microsoft and Google and there's a whole bunch of other companies that offer similar services, and they all use VMs. Another thing that is really cool about a VM is that it actually gives you the ability to pause or checkpoint or create snapshots. So let's say you're playing a really hard game that doesn't have save points. Okay. So I can pause in the middle of my battle with Sephiroth. I can pause by pausing the VM. And I can come back later. So let's say that, I'm at the end of Final Fantasy VII. I'm playing, it's the final battle. And, I forgot I had a cake in the oven. I need to go deal with that. But I can't pause in the middle of the game. So I pause the VM instead. Checkpoints and snapshots. You can continue that later from that exact saved position. So there's lots of really cool uses for VMs. Really, really cool uses. We don't have a lot of time to talk about it, unfortunately. All right. So that is the end of the official course material. However, as I said, we are still going to have 2 more episodes next week. They are bonus content. One of the topics is going to be networking. We're going to talk about some other fun assorted things about operating systems, but will not be covered on any final assessment. So it's your choice whether you tune in next week. I hope, though, for those of you who decide not to tune in next week, I hope that this first all online offering of 350 has been a reasonably pleasant experience for you. I know we've worked hard to try to make sure that this is as seamless for you as possible and that there's something more. We wanted to give you a fun experience, so I hope that you've enjoyed it. Tune in next week, maybe. Otherwise, good luck with your future studies. On our next episode, should you choose to tune in, networking. So we will see you then.
Hello? Hello?
Hello?
Hello?
Hello.
Hello?
Oh, hello, Barney.
Hello? Hello?
Hello.
Hello?
Bonjour.
Hi.
How you doing there? Yellow? Hello?
Hello.
Hello?
Hello.
Hello.
Yo.
Hello?
Hello.
Hello?
Hello.
Hello?